Okay, this is a quick video about rockets. You may know that an airplane accelerates forward by pushing against the air, but rockets work in outer space. So the question is, how does a rocket accelerate if it has nothing to push against? Okay, so this is what we're going to try and figure out in this. So I want you to consider something completely different instead. So here's a picture of someone in a shopping cart holding a big rock. What happens if the person throws the rock to the right? Well, the rock will go to the right and the person in the shopping cart will start moving to the left. Why is this? Newton's third law. The person exerts a force on the rock, which pushes the rock forward, and therefore, by Newton's third law, she will experience a force to the left that is equal and opposite. And they will keep that motion and continue on. Instead of thinking of this in terms of forces, I want to instead consider this problem from the point of view of momentum. So right now, both the woman and the rock are at rest. That's to say that the system has no momentum. Momentum is conserved, which means that no matter what happens after this, the total momentum of the system has to be zero. So that's to say that if the rock all of a sudden starts to move to the right and has positive momentum, the momentum of the woman must exactly cancel the momentum of the rock. Okay? So how does a rocket work? Well, a rocket is filled with rocks, and it throws the rocks out the back and thus accelerates itself forward using the same principle of conservation of momentum that we were talking about before. Of course, there's not rocks. They have some sort of gas or something, and they heat it up and it shoots out the back. But the idea is the same. The fuel that gets shot out the back has negative momentum. The rocket ends up with positive momentum. One of the things we're going to have to be careful about when we do this mathematically is notice this m of t. The mass of the rocket changes as more fuel is thrown out the back, and that creates a little bit of a headache. We're going to figure it out. It's not a big deal, but that's why the math is going to look the way the math is, okay? So I want to abandon that picture of the rocket and just start very simple. Let's assume that we have some big block, and this block is going to throw pieces of itself away, like this. Okay, so they both started at rest. Now the block is moving to the right with a speed delta v, and this little block is moving to the left with some speed v. Well, the momentum of the system has to be zero, and so what we say is that the total momentum is zero before, and it's zero after. If we do a little bit of algebra and we solve for delta v, well, delta v is delta m over m minus delta m times v. It's some stuff, right? Okay. What happens if it throws another one? Something to consider this time is this object, when it throws the second rock, is lighter than it was the first time. That means it's going to have a different effect on the velocity than it did before. In fact, now it has delta v1, but since it's thrown another rock, now it has delta v2. One other thing that's a little weird is that this block did not start at rest. This block started with a speed delta v1 because it used to be part of this block. Now it's still being launched back to the left, but it has a speed to the left minus the speed it originally had. So these are the kinds of headaches that we're going to have to deal with. I have written the algebra beneath. The algebra essentially looks the same as it did before, except we've got some delta v2s and such. You can pause the video and look at the algebra if you wish. The point is, the big takeaway is that the change in speed now this time looks a little different than it did the first time. Notice this factor of 2 here. Notice the factor of 1. So delta v1 depends on 1. Delta v2 depends on 2. In order to make this block move fast, ultimately we're going to throw n of these blocks off. So we'll throw a bunch of them off. And we'll come to the conclusion that the change in speed depends on how many blocks we've already thrown off. So you can see the denominator is actually getting smaller, which means that the change in speed gets larger every single time. So what does this mean? We don't want the change in speed. We want to know, okay, how fast is this object going? What's v? How do we get v? Well, we have to add up all of the delta v's. So if we add up all of the delta v's, we end up with something that looks like this. Now, you may say something like, what is this delta m? Like, how do you know how much that is? Well, you could make the decision that if you start with some initial mass and you end with some final mass and you throw off n chunks, then each delta m has that fraction of the mass that you've lost. So we could plug that in. If we do, it looks pretty hideous. So maybe what we'll do is we'll go back to the original formula and just say that's what we mean when we say delta m. Now, we could do this sum, but it's kind of annoying. Sums in general are difficult to do. And also there's a kind of deeper physical problem here, which is I'm assuming each time this guy gets thrown off that it kind of happens instantaneously. But that doesn't really make any sense. It takes some time to throw this thing off. And if you acknowledge that as each block moves off, it changes the way that it affects this thing, then we kind of have to see each block as a process rather than an individual event. In fact, the only way that I could think of this block being shot off instantaneously is if it were an infinitesimal amount of mass. So great, if I am willing to shoot off infinitesimal amounts of mass, I can do it instantaneously. But you know that if I'm doing infinitesimal bits of mass, I'm not going to be doing a sum anymore. Somehow we're going to have to do integrals here. But that's actually good news because it makes the calculation easier. So I'm going to do the same thing I did before. I'm going to have a little piece of mass dm, only this time I'm going to say, look, this thing is already moving. This has been going on for a while. Let's see what the effect is of having one more shoot off. So I have one more shoot off, and now this, as before, moves with a speed v minus ve, because it was already moving before, and this has a speed v plus dv after the collision, okay? So if I look at the momentum afterward versus the momentum before, and I do a little bit of rearranging, a little bit of algebra, I end up with something that's actually not too bad. It does have some differentials in it, but that's not too big a deal. The only thing that we want to do is we say, look, this dm, that's the amount of mass this thing has. But how does that relate to m? Well, m is decreasing by this amount dm. So we make the statement that dm, which is the amount of mass that the little block has, is how much mass gets lost by the big block. So that's why I made that little substitution there. Okay, here's the calculus part, right? We just say that dv equals dm over m. So I put everything involving m on one side, everything involving dv on the other. Ooh, oh no, I forgot my ve. There's a ve there too, okay? And then if I do this there, my ve magically reappeared. So there's my ve. You'll end up with an expression that looks something like this. Okay, so what does this look like? We have one expression involving a sum. We have another expression that we got doing an integral. It's the same idea. I just, instead of having chunks of mass, I had little tiny bits of mass in this case. You may be like, I'm not convinced. I don't know that it's really the same thing. If you're skeptical, I made a little plot. So what does this plot show? This red line is this result that you get just by integrating. The blue line is taking different values of n and trying to come to the same final mass as I did. If I have very few trials, in other words, if I shove the mass off in big chunks, I only throw 3 chunks off, well then yes, the results are quite different. But as I take that total amount of mass and I break it into tinier and tinier chunks, then these two formulas actually look exactly the same. That's actually good news, because if you're doing this on a computer or something and you want to simulate it and you don't want to do calculus or anything, you can do it. Just make sure that you have lots and lots of trials and you'll end up with the same result. Okay, anyway, this is the main thing you're going to want to use. I just want to show you one thing you can do with this, and that is take its derivative. This is the velocity. What if you want to know the acceleration? Okay, if you take the derivative, then you take the derivative of a log, which looks like 1 over the inside, and then it gets complicated and ugly, but it ends up looking something like this. You can pause the video and work through it if you like. Okay, and then more importantly, if I multiply that expression by m, I end up with something that looks like ma, and that is a thrust. In other words, I can now talk about the force that the gas exerts on the rocket, and that is remarkably simple. In other words, the force that is thrust on the rocket just depends on dm dt, which is to say how quickly I burn gas. If this minus sign bothers you, remember that dm dt is also negative because it's decreasing. So overall, it's a positive effect that pushes you forward. Okay, so these are the two main equations you'll use in rockets. And let's do a quick example, right? Let's say that you've got a rocket traveling in outer space, and it's far from gravity. We don't want to have to worry about gravity because I haven't said anything about gravity yet. And we say the initial mass of the rocket's 10,000 kg. How much does it have to burn in order to get from rest to 100 meters per second? And let's just say that the exhaust speed is also coincidentally 100 meters per second. You know, in real life, the exhaust comes from, you've got some gas and you light it on fire, and these things are moving around like hotcakes, and you just have a little hole here, and accidentally some of them get through. So the exhaust speed, in some sense, depends on the temperature in there. Okay, that's really beside the point for our purposes. We don't need to engineer this. We're going to take the lazy route and just be physicists and say the engineers have already done all that work for us and told us how fast the exhaust speed is, and then we'll say how fast the rocket will go. Okay, so how do we do that? All right. Well, we have this equation: the speed equals the exhaust speed times the initial and final mass. We want to know how much fuel we have to burn. So in some sense, they're looking for m of t. Okay, so 100's our final speed, 100's the exhaust speed by accident, right? Or I rigged it that way. Okay, and then here's our initial mass. If you solve a little bit, right, you end up with E over M, which is about 3,678 kilograms, okay? Which is actually very interesting. You've burned most of your mass to get to 100 meters per second, and I'm going to tell you 100 meters per second isn't even that fast. That's pretty slow. So the good thing about a rocket is it can fly in space. It doesn't need to push off anything. The bad thing is it needs to bring all its fuel with it so that it can push off of its fuel, and it needs to bring a lot of fuel. In fact, most rockets, rule of thumb, they say for rockets, when it leaves the Earth, 90% of the mass of the rocket is its fuel. In other words, you have to bring 10 times as much weight just to get the weight you want off the ground. Okay, so that's an example of this. This is a twofer. I want to use this equation to do the exact same problem. So let's do that. So now we'll just talk about the thrust. The problem says you want to produce enough thrust to mimic gravity on Earth. Okay, that means the thrust is like weight. Okay, so that's the force of thrust. So what are we saying? We're saying that dm over m equals minus g over v dt. We do a little integral and you end up with the log of mass equals something that depends on time, more or less. And so what we want to solve for is m. We're still after m as a function of t, right? And so we can rearrange this a little bit and you'll end up with the mass now decays exponentially. This is interesting if you just think about this plotted. So this is m as a function of time. We start at some initial mass m initial, and decaying exponentials look like this. They change very quickly at first, and then they slow down their rate of change later. Why is that? Because when the rocket is heavy, when there's all that mass, you need to burn a lot of fuel in order to accelerate it. As the rocket gets lighter, you don't need to burn as much fuel anymore to keep producing the same acceleration you did before. Okay, anyway, we can plug in the numbers. It takes 10 seconds accelerating at 1g, so that's 10 meters per second squared. That takes 10 seconds to get to 100 meters per second. So it takes 10 seconds. If you say, what's m of 10 seconds? Well, it's 10,000 times e to the 1. Obviously, we got the same number as we did before. So that's an example of how to use both equations actually on the same problem. And then as an added bonus, I said we weren't worrying about gravity before. Well, let's worry about it and see what happens. The beauty of writing this formula this way, F thrust, is that now this effect of throwing its mass out ends up being just another force on the rocket. And so if I want to include gravity, well, now I have mass times acceleration equals the thrust and then minus this effect due to the weight. And so in this case, we have a little bit more calculus to do. We'll do a little bit more integration. Notice it's a little weird because you've got m of t. These things are annoying, but notice we can cancel them out. So if you get rid of m as a function of t, they cancel out, except in this one. Okay, and then our plan is to integrate this with respect to time so that we can recover v. Okay, now this is the one trick I wanted to show you. So this is dm dt here, but I'm going to have a dt that I multiply everything by. There's the dt that I multiply everything by. And what I did was I was really sneaky. Instead of writing dm dt times dt over m, I wrote dm over m times dt over dt, and then I cancel those and it becomes the integral of dm over m. It's a very sneaky trick. Anyway, we can do this integral same as we did the last ones, and you'll end up with something that looks like this. Okay, so the reason I show you this is just to show you how you can incorporate this into a more complicated example, but also there's something interesting here. Notice that the longer you spend thrusting, the more speed you end up losing to gravity. In other words, if you have a rocket and you want to lose less speed due to gravity, then you should do it quickly because time is explicitly a factor here. So if you make t small, right, then you will lose less velocity due to gravity. So how do you make t small? By burning the crap out of all your fuel right at the beginning. And that's why when you see rockets launch from Earth, they have tremendous explosions. They are doing their best, not just to get the rocket out of Earth's gravitational field, but to get it out of Earth's gravitational field as fast as possible. And that means creating tremendous thrust and tremendous acceleration. Okay, anyway, hopefully this video was more helpful than confusing.